Hello everyone, my name is Tong from Wajin Tech, and today I'm going to present our work PAX permission check analysis framework for Linux kernel. My advisors are Dr. Dong Li and Chang Heijun. This is a joint work with Dr. Wen Boshen and Ahmed Azab and Rowan Wang. And so permission check control in Linux is complex, and currently there are 3 different control models, and the first one, as we all know, is very common, called DAG, which is file-based permission. And the second one is called capabilities. That one is invented to break down the root permission into, currently we have 38 different capabilities. And here's one example. So the ping command used to have the full root permission, but now it only has the capability of sending raw network packet. So, and the third one is called LSM, and that is short for Linux Security Module. And as well now, we have 190 different hooks in the Linux kernel. And they are used to implement SE Linux and APP Armor used by lots of defense mechanisms. And because that those hooks are actually added into the Linux kernel in an ad hoc manner, and so that is hard to guarantee all of them are placed correctly, and this is the motivation of our work. Next, let's look at one example. So this example is showing the method to change a process name. So usually we can have the first method is to use the so-called proc file system. There is one file called comm. As you can see here, I draw a path from the user space, the write, and we can call the write to the comm file. It has to pass a security file permission check in order to invoke the set task comm, which will eventually change the process name to a new name. And there is also another way, so that is to call the so-called process control system call directly to change that name. And that system call will call the set task comm directly without passing any checks. So you can see here we bypassed the security file permission check, which is actually a problem. So our goal here is to design a static analysis tool to find out all of those kinds of permission check bugs, including the missing checks like I showed here, and inconsistent and redundant permission checks. In order to do this, we need to enumerate all the possible passes that can be reached by a user. And luckily, we can see those possible passes can be represented as a control flow graph that I showed here. And then our problem becomes, can we enumerate all the passes using this interprocedural control flow graph to find out the possible bugs? And before we do that, and we actually need a interprocedural control flow graph. How do we get that? As we all know, this is the first challenge. As we all know, in the Linux kernel, there are lots of indirect function calls. So we counted in the version 4.18.5, there are 115,000 indirect call sites. And kernel frequently use those function pointers to call the real implementation of either its file system or the driver. So it's to call from the abstract layer to call the concrete implementation. So for example, we have a VFS layer. It is calling the from the file, it is calling FOPS and then write either. So the possible target could be exe4, BTRFS, CIFS, or the NFS. Similarly, we can have the network layer. It is calling the send message according to different protocol that you are using. And however, there are no existing that working solutions. One of the solutions that used up by prior work is to use a type-based approach. So it is also known as the function signature-based approach to resolve the indirect cause. The downside of that is that it's imprecise. For example, still the VFS right example. If we look at the function type or the function signature, we can find out that the right function is actually the signature is actually the same as read. So if we use function signature, this will result in a wrong call graph. And another approach that people have tried in the prior work is to use advanced pointer analysis. That does not. That will also contain the pointer resolution for not only for the function pointer as well, and also data pointer as well. So the problem of this advanced pointer analysis tool is that it does not scale well for the size of the Linux kernel. So there are like 16 million lines of code. So the existing tools like the SVF does not scale well. And the people have tried to break down the kernel code into smaller pieces so that they can apply the SVF in a more scalable manner. And that downside is that it will harm the soundness. So that means the interprocedural call graph will be, control flow graph will be not as sound as the previous one. And the challenge 2 is actually a result of the ad hoc manner of adding those permission check functions or hooks. So the first thing we don't know is that the security permission check function is added in an ad hoc manner. We don't know that. And the second thing is that we don't know which function is actually intended to be protected by those security permission check functions. And the third thing is that we don't know their mapping. So those are the three things as a result of the ad hocly added the permission check function. So we need to solve those two challenges. All right, let's let's take a look at how the PAX works. The PAX takes into the kernel source code compiled as a IR. The LLVM IR, and we first run a key ring, which is responsible for resolving the indirect call and draw a interprocedural control flow graph. And we use that interprocedural control flow graph to solve the second challenge, which will allow us to detect all the permission function wrappers and the privileged functions, which is actually intended to be protected by permission check functions. And finally, we will use the ICFG and also those mappings we generated to detect the error. So next, let's take a look at how the key ring works and how do we actually resolve those indirect calls. The keyring is actually designed based on the observation that most of the indirect calls, we counted the number, about 90% in the Linux kernel is actually using a well-defined the interface that I just talked about. And that means, so give you an example. So for the file system, we can have the structured file operations. And the kernel developers, for example, the file system developer only need to worry about those functions in order to, integrate their own the file system into the kernel and without worrying about other parts in the whole file system stack. Similarly, for the network protocol, we only need to worry about how to implement the send message, receive message, and so on. So, so the keyring is actually designed to take advantage of this, and it can be implemented in the two steps. And the step one, like I just said, the kernel have a well-defined such interface. The thing we need to do in the step one is to collect all possible target for those function pointers in the such interface. So we can see for the proc file system, we can have the COM right being assigned to the right function pointer there. So similarly, we can have exe4 and VFAT and other file system. And so keyring basically keep track of all those statically. You can see here it's statically initialized, and we can also have a dynamically initialized structure as well. And keyring basically keep track of all those. And once we have all those information, the thing will become much simpler. And the thing we only need to do is to look at the call side. First thing for this step 2 is we need to identify such interface. And so you can see this VFS file write example. We are actually using this file operations, that interface, and we are calling the write, using the write function pointer inside that interface. And then we can draw a conclusion that this line is actually trying to call a function pointer that assigned to that write field. And based on our this step 1, we can see the possible callee for this FOP write is COMM write. So this is how the keyring works, and it can help us to solve 90% of the indirect cost, which is pretty good. So the advantage of this approach is that its precision is better than the type-based method. As I just showed in the previous example, the type-based one will possibly point the write to some read function, which is actually incorrect. And if we compare our keyring approach to the existing SVF-based approach, we can find out that our approach is much more simpler and more scalable than the SVF-based approach. So let's take a look at the rest of the PAX workflow. So next, I'm going to talk about how we solve challenge 2. So we actually require the user to give us some seed input for the permission check function. And then we will run the analysis on the ICFG we generated to detect all the function wrappers to that permission check functions. And we use that detected permission check function to detect all the privileged functions. So we want to know which function is actually protected by those permission checks. And in the next couple of slides, I will focus on how we actually detect the privileged functions. In order to detect the privileged functions, we run the analysis on the interprocedural, the control flow graph. And the first requirement for that is that path had to be user reachable. All right, that's no doubt, right? Otherwise, there is no way to trigger that. So the second thing is that the call side of a protected a permission check function should dominate another call side that I showed in the green box right here. So you can see, without going through the security file permission, that is a permission check function call, we cannot reach another call side, which is FOP write. So that means the FOP write is actually protected by the security file permissions. And then we will mark the callee of such the green box as the privileged function. And however, if we have another outgoing edge from the security file permission, let's say it can call some function called bar, and there is another incoming edge from somewhere we don't know, and then so that means without even going through this permission check, we can still call the function bar. Then we can now draw the conclusion that the bar is the privileged function. So that's a result of the privileged function detection. And then we can use those information that we collected and run the analysis on the interprocedural control flow that we generated using keyring. And we can see in the first step, we use the permission check function, and we got the privileged function in the at the very bottom. And once we got that information, we will run a backward analysis to see whether we can reach a system call entry point. And for that, exactly the path, if we found out that there is no permission check function call, then we will, the PAX will raise an alarm. For implementation and evaluation, we implemented PAX using LLVM and generated a single VM linux.bc file using WLLVM. And we evaluated the latest stable Linux kernel at the time we write the paper, and we used two different configurations for the for testing. So it's a default configuration that contains 2.4 million lines of code, and OES config, which contains almost 16 million lines of code. And next, let me show the detection capability, which is the most interesting one. As we can see, the PAX key ring, which is our work, will detect 21 bugs. For the PAX with type-based indirect call resolution, we will also detect 21 bugs. But for the key minor plus the SVF-based approach, we can only detect 6 of them. That is because the way that how the SVF is actually applied can generate a unsound intra-procedural control flow graph. And although we can see here we have the same amount of bugs that detected at the PAX type-based one, for the next slide here, if we compare the number of warnings that generated by type-based one and PAX keyring, we can see the PAX keyring actually generates a way less number of warnings than the PAX type-based one. That means the programmer need to spend less amount of time parsing all those warnings to find out the real bugs. And there is no surprise that the PAX K-minor-based approach generates less number of warnings because the unsound ICFG generated by them. So to conclude, PAX is a static permission check analysis framework for Linux kernel, and keyring is a very effective way to build an inter-procedural control flow graph for kernel analysis. And we also produced a list of permission check functions and privilege functions for developers to use, and we evaluated the latest stable Linux kernel with PAX and found out the 36 permission check bugs. And that's it. Thank you.
We have time for about 1, maybe 2 questions while Anho gets set up.
All right, John Criswell, University of Rochester. Nice talk. One question I have about Kirin is the call graph analysis that it's performing. Is it taking advantage of Linuxisms? So, for example, the fact that these global data structures are initialized once, and then it assumes that it's not modified.
Yeah, most of them are actually initialized and then set to the read-only. And there are cases that the device driver can be dynamically configured. So there are also cases those fields are dynamically initialized. So we also keep track of that.
Right, but you assume that they're not modified after initialization, correct?
Yeah.
Okay.
Yeah, that's possible. Yeah, it could also be modified, but that's rare.
Okay.
Yeah.
Thank you.
Yeah.
Hi, thanks for the talk. It's Mohammad Saeed Talebi from UC Irvine. My question is, when there are multiple candidates for a function pointer in building your control flow graph, how do you choose among them? Because the data structure that you show, maybe in some modules there are a couple of them, and you can't know which one to choose for the function.
Yeah, I think probably we'll run out of time. We can take it offline.
Okay.
Yeah.
Yeah, let's go ahead and take it offline. All right, thanks. Let's thank our speaker once again.